Hello everyone. Today we're talking about big O notation. This big O notation is very important for coding interviews, and if you're taking a data and algorithms class, it's going to be very important there too. So, what is big O notation? Big O notation is a way to describe the performance of an algorithm to the input size. So, here we're talking about a couple of things, two things actually. Time, which is going to be the big thing here, and memory space. But the most part of it, think of it in time. Yeah, that's the big thing we'll be focused on in this topic. Oh, I know, and I forgot to mention in this big O notation, there's sometimes on YouTube there's like these functions f of n and g of n, but I'm not really getting into it. It's mostly going to focus on the data structure and what's its uh, big O notation. Um, I'll get more into that later. So I'll give you an example of binary search. If you're not sure how binary search works, definitely go to a video and find an example and try to do it out. I'm not really gonna go into it in this video, but what I am gonna do, I'm gonna talk about what's the big O notation for binary search. And so, like I said here, it's a quick way to find a number or a key if it's inside a sorted integer array. I'm using numbers in this sense. So we're looking at the number of items versus the number of comparisons. So the number of items is the input size, number of comparisons, number of operations. So by uh, the input size, we're talking about how much data do you have. In this example, binary search, how many with the numbers that were given in an example, um, how many comparisons, how many operations can I do? How can how do I explain this? It's kind of like saying what comparisons. It's like how much time it takes to execute the binary search uh, with the input size, basically. So it's like saying, okay, I have binary search on some array. How long will it take? Now, I'm not talking about time here. I'm talking about uh, the the function of binary search. By function, I mean how the binary search works is what I'm talking about. And so in here, um, again, I'm not gonna do an example. Try to do like simple ones, maybe like with 5 elements or something even, maybe like 6 elements. You don't have to do 100. That's gonna be taking you way too long. And so, um, I'll post a video for the link where I found a good resource for big O notation. And so we have 10 items. You're gonna have four number of comparisons. We have 100. You're gonna have seven. The question here is, what if we have n items? What will be the number of comparisons? Because the important thing here is like if I have a million, if a billion items, how I'm gonna figure out the big O notation of that? Well, it's gonna take us a long time if we do it, sorry, by hand. And so this is where we're that's where we're kind of getting into like if we have n items, what would be the number of comparisons? So let's say we have 100 items. They're like boxes here. I'm gonna show you in the example below. They're gonna be boxes. So this 100 items are gonna be box. This 50 items is gonna be box, 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 all the way to one item, which is also a box. So what happens here is we cut the array in half. We get rid of what we don't want in binary search, and we look at the where that key is, if that makes sense. If not, please let me know in the comments. I can explain, put a video on that if you want. But there's plenty of other YouTube videos for that. But if you guys want, I'll do it. I don't mind. So if I have 100 items, we're going to have 50. If I have 50, I'm going to have 25. If I have 12, I'm going to have 6. If I have 3, I have 1. So realize here, when we get to 3 to 1, we're not like, so we're dividing by half. 3 divided by 2 is like 1.5. But what's half a number? That doesn't make any sense. If that makes sense. Like 1.5 is like 1 and one like number and half. That's why, like, you see this is a 1, is not a 1.5. And so, if you count the number of boxes here, we're gonna have what, 7? 1, 2, 4, 5, 6, 7. So we have 7 boxes, meaning we have 7 number of comparisons. So now, that's how I got the answer before in the table. Yeah, right here, you see 100 items, we have 7 number of comparisons. The same could be, you could do the same thing for 10, and you'll figure out it's gonna be 4 number of comparisons. Um, oops, sorry, 1 second. And so in here, I mean, the question, what if n items? What are the number of comparisons here? So what we're gonna do, we're gonna follow the same idea like this, like the 100 items example, sorry. And so every time, I go through the array, I'm cutting it by half. So n items, and I'm gonna divide it by 2. Okay, I'm gonna divide by 2 again, which is gonna be n over n divided by 2 squared. I'll get into the reason why I'm doing 2 squared and not 4. And so, uh, yeah. And then we keep going to 3 divided again, gonna have 3 all the way into like 2 to the k. So this k is a number, it's a constant. So, well, in this sense, it's a constant, I should say. And so later on, we'll figure out what this k is, because that's kind of the goal. This is the number of comparisons. If you look at the exponents here, they all have powers, and think of the k as this 2 and this 3 as a power. And so going down here, I'll explain why. So some people like to write fractions like this, which is totally fine. If it doesn't make sense to you, you can think of it like this. It's the same idea. So if we do n divided by 2, n over 2 divided by 2, we use KCF, change the multiplication, and flip this to 1 over 2, and you get n divided by 4 as an answer. The reason why we have it in squares, because the pattern is if I do n divided by 4 and then divide by 2 again, it's going to be n over 8. Um, it's just a trick to see. It's another way to write the exponents. It's just a way to figure out if I have n over 4, n over 8, right, and so forth. What am I figuring out with just those numbers, if that makes sense? That's kind of like I thought of exponents. If you think of exponents, you kind of figure out, okay, there's some power here we have to figure out, or some constant we haven't defined yet. That makes some sense. And so we have k plus 1 boxes in total. Because if you look at from n over 2 to n over 2k, that's k boxes, right? Because as you have from 1 to k, that's k boxes, right? This is power to this 2 is to the power of 1. You just don't see it. And so if you include the n items, that becomes k plus 1. Okay? And so when we're following the example of 100 items, we're saying that sorry, let me go up a bit. So from this example, we're looking at this example again, 100 items, but we're looking at this one and this last box here. These two last boxes, we're saying they're the same. They're equal to each other. And so when we do that, we're gonna get, oops, what happened? Oops, sorry guys, I don't know what happened. Give me 1 second. Sorry about that. Okay, there. Sorry about that. Some glitch. And so, oops, I went too far. Sorry. So now we're saying like this. N over 2k equals 1. We multiply it, Oh, I forgot to mention, guys. Oh, I'm sorry. If we use k plus 1 boxes, right, that's 2 to the k plus 1. The thing is, if you can do it like that, that's totally fine as well. The thing why I left that as 2 to the k is just to simplify the problem. It's because at the end, right? I'll explain it once I get to the calculation. So it's 2 to the k times 2 to the k on both sides, n equals 2k. And now here we use logarithms. If you guys don't remember logarithm, that's totally fine. Just go find a YouTube video or something to help you refresh your memory on that. Uh, I use base 2 because I'm trying to get rid of the 2 here. And if you guys want me to do a video on that, I can definitely do that. That's no problem. And so And here, we're going to have take log on both sides. The k comes down because of log properties. So be k times log base 2 and a 2 here. So that becomes 1 when you have the base and the number being the same. That becomes 1. So you just figure out k is log squared n. So therefore, if I have a number of comparison of n items, it's log squared n. Sorry, I don't know why I keep doing that. And so the runtime for binary search is O of log squared n. I hope that was kind of clear. If not, let me know. I can definitely explain in the comments. And that's how I figured out like binary search is log squared n. And so I'm going to move on to the next example, linear search. I think this is a little bit easier, but I understand it's not this simple. I know me and binary and big O notation was something that like threw me off in the past, but after I spent some time with it and I really like try to do it on my own and I look at some videos and stuff like that, but I also do it on my own, kind of have a better understanding of it in some sense. Uh, but I hope this will be kind of clear. So again, we have 10 items, we have 10 number of comparisons. We're looking, again, linear search, we're looking for the array. It's like binary search, but in the difference here in linear search, we have to look through the whole array. And so we have the same question again with n items, what will be the comparisons be? In this sense, if you have the 6 here, right, we're trying to figure out if this is in the array using linear search. So I'll go through, okay, is 6 here? No. Is 6 here? No. Is 6 here? No. Is 6 here? No. 6 here? No. So I use a small example, I use 5. So if I have 5 items, I'm going to have 5 number of comparisons. I hope that was clear. So if there are n items and there are n comparisons, so our running time for linear search is O of n, where n is the number of operations the linear search took to execute with n items. The same could be said with like binary search, where this n in log squared n, where is it? So this n in the binary search here, it means the number of operations it took for binary search to execute with n items. I hope that was clear. If you guys have any questions or anything at all, let me know. As I always say, keep practicing. Try to do it on your own. Try to make an example or use an example from a video, and then figure out if you got the same answers to person. That's another way. If that helps. So again, take care, everyone. Have a nice day. Stay tuned for more. Thank you.